So let's start. My talk is going to be split into two parts. The first part will be about enhancing your application development. And let's start with the basics. So you're developing a NoSQL application, and the first thing you're told, you need to define the queries. What are you going to query? When you have the queries, you're building a data model around those queries to answer them. Then comes a choice or a point where you need to decide. Some people select to run Cassandra tests or other simulation tools to see if this really holds. Others select to develop. When you do your development, you start running small tests, and the reality is that you need to do some iterations. The queries are not correct, the data model needs updates, and then you can continue. Last year, we talked about SQL optimization and what it can do to help you recognize items in your application early in the cycle. So we can tell you ahead of time that you're doing things wrong, and we also tell you items that you need to reconsider. Once development is done, or at least a portion of it, you move to scale testing. And the reality is that many times you find yourself with large partitions, and that requires changing the data model, adapting your queries, and handling them. So finally, we finished the development, and we're ready to deploy. And once we deploy, we find that we have hard partitions, and we need to deal with that. So we change our queries, change the data model, everything is great. So today I'm going to talk about disk access and what this can do to help you develop your applications. So when I talk about disk access, what I'm looking for is what would it take to answer your queries if I was doing it through the disk? And where would it fit in? So it fits in right after I have my queries and my data model. And in the talk, I'm going to try to convince you to use it. So if we look a bit further into disk access, when we talk about doing operations on the disk to answer your queries, we're actually counting two different items. We have I/O operations, and we have the amount of bytes that we need to read off the disk. And in the case of Scylla, reading the information to answer your queries is off SS tables. So there are many components for the SS tables, and only two of them reside on the disk. We have index and data. The data simply stores your data, so that's easy. The index is a lookup table into the data file. And why are we interested in disk access? So let's look at the trend. So the ratio between memory and disk is increasing. If we look at AWS, they had i3 instances over a couple of years ago that has 1 to 30, which means that for every gigabyte of memory, I have 30 gigabytes on the disk. Last year, they introduced the i3N family, which is 1 to 78. For every gigabyte of memory, I have 78 gigabytes on the disk. So that means that a larger portion of the queries will be read off the disk. But that's not the only reason. When we talk about analytic workloads, we're actually looking to do them off the disk. We want to allow our online workload to be processing and working, and in parallel to do the large scans. So to convince you to consider this, I need a sample application. And we're going to talk about Billy. So Glauber and the keynote session talked about an IoT application of 1 million sensors, and the code name for that application is Billy, hinting on what we were looking for, reaching more than 1 billion operations per second. So just a reminder, we were looking at a 1 million sensor application recording data over a year, and samples have to do with 1 per minute. Scylla can handle online workload for this great, but Glauber was trying to do analytics over this workload and prove that it can be done fast. Then he had a great picture, and I stole it. But the point is that Glauber showed you that we really can do it. We haven't done it before. My talk is to convince you that with Scylla 3.2 and future releases, this can even be done better. So the data model. We have a sensor ID and a date. Those compose our partition key. We have time, and for each minute, we're recording a temperature. The queries that we can get with this data model for a sensor and a date, what are all the readings, or we can drill down to a specific time range. So analytics option 1 is basically doing the following query. We want Scylla to compute over all the rows of a sensor and a date what is the minimum and the maximum. And if we're talking about the applications that Glauber presented, we have a coordinator node that splits up the 365 million partitions into different workers. Those do the queries on Scylla, get the minimum and maximum, do a partial result, and returns that back. Let's do a theoretical analysis. And since I want it to be easy for me and you, I have some very simplifying assumptions. So we're going to assume that a partition, again, a partition is a sensor and a date, and all the readings is going to be stored on a single SS table. And in addition to that, it's going to be perfectly placed on a data block. So every data block is a single sensor reading. The other assumptions that I'm using is that Bloom filters do not provide us false positives. So if I'm going to an SS table and through the Bloom filter, it means that the index will always return that the partition exists on the disk. So the analysis is simple. To read all the sensors, I need to do 365 million SQL operations. If I'm talking about the IO4 index, it's 365 million. If I'm talking about reading data blocks, again, it's 365 million. So the goal of my talk is to push this down. And what is the option number 2? So option number 2 is going to use SQL group by that is going to be in part of 3.2. And what SQL group by allows you to do is to condense multiple rows into a single row. So if I have a set of rows condensed and an aggregate function, that will be operated over those rows. So basically, my query is going to be compute the minimum and maximum while, let's skip this part, while I'm grouping over sensor ID and date. Okay, which is perfect. I'm getting a minimum and maximum for each sensor and a date. Why do I need token ranges? Because I want it to be optimal. I want to send that query to the replica that has the data. So the application is very similar. The application needs to know the token topology of the cluster, then break up the huge range into subsets of queries. It's going to send that to the workers that are going to query the database, returns this back, and we have our result. So let's analyze the disk access, theoretical disk access of option number 2. And it's using the same assumptions. So the number of scans that we need to do is the number of vnode token ranges. The number of IO for index is the number of vnode token ranges times the number of shards. So when Glauber was doing his single partitions, they were directed to a single shard. But when we're talking about a token range, then that token range is split up across all the shards in Scylla. If we're talking about reading the data, it's exactly the same. So we need to read all the data blocks for the sensors. And let's compare the two. So in the use case, they were using 83 nodes and using a number of tokens of 256. So that means the number of scans was around 21,000. If we're talking about IO for the index, then we take the number of operations that we need to do and multiply it by 54, which is the number of shards. So it's around 1.1 million. And the number of IO for the data is exactly the same. So we have a very large reduction in the number of SQL operations that we need to send to Scylla. Again, that's additional processing. And the number of IO for the index blocks. So let's talk about the theoretical gain. So the number of IOs for the index just dropped, but in reality, the difference is going to be even bigger. And that is because Bloom filters are not perfect. We're going to get false positives. So we're going to go to an index file and find out, well, the Bloom filter was incorrect, and the partition doesn't exist in the SS table. The next item is the number of SQL operations. Now, the computation was very optimistic. If we have 365 million partitions divided by page size, the default page size of 5,000, we end up with 73,000 pages being returned. That cannot be done with 22,000 queries. So the minimum, if we're using the default page size, is 73,000. So it has to be bigger. But we're not going to reach the 365 million. Last, well, the biggest assumption that I had in the theoretical was that a partition is perfectly split across the data blocks. They're not. They're going to be scattered around and so forth. So let's try to actually simulate this and verify that we want to use range scans with SQL group bys. So let's put it into practice. So what do we need? We need queries and data model. We need some test data. We need Docker and Scylla nightly that has the image of 3.2. Scylla 3.2 added something to make this accessible for you. So we enhanced tracing, and we added into the tracing the data I/O that we're doing. So if you'll use Scylla 3.2 and trace a query, you're going to see, you're going to see lines like this. The index file was read, and then the amount of data that was requested, and what actually needed to be read. And that's it. Well, you can use a paper and pen and then compute everything, or do what I did and write a simple script to get your results. So let's test this for Billy. So I selected 1,000 sensors instead of 1 million. I selected 100 dates instead of 365, and I used the same partition size. So keeping that to make sure that the simulation I'm doing will be close to reality. In total, we have 1 million partitions and 1.4 billion rows. The number of shards that I used was 4. So running the simulation for Billy on the data set that I created, I got the following. The index was 1.3 million. The index bytes read were 2.8. And the data I/O was 1 million. And the data bytes was 14.4 gigabytes. OK? Anybody can say if it's good or bad? Well, I can't. I need to compare it to something. So I then ran the same test using range scans. And we can see that the index I/O and the index bytes dropped significantly, okay? Which aligns with the theoretical gains that we were expecting. But the data I/O dropped also very significantly, and the data bytes was a huge gain. Instead of reading around 14.4 gigabytes, I was reading only 1 gigabyte. So it's 11 times less than the partitions, single partition. OK, so going back to our gains, so there are even bigger gains when we're talking about doing full scans. So Scylla will apply read aheads. And read aheads are basically when Scylla detects that you're doing a sequential scan of a data file, it will fetch the information before you request it. So it will be even more optimal. If we're talking about the number or the buffers that we saw and the fact that the amount of data I/O was much less, is because we were reading larger chunks. So when we're talking about single partition average data bytes request, it was around 14.5. If we're talking about range scans, we were using 126K buffers. So again, it's much more optimal for some cases. Last, I/O reads. So we're requesting from the disk, or we're sending requests that are specific. We want to read 538 bytes off an offset 0. But the disk doesn't work in this. The disk has to function in blocks. So even though that I requested 538 bytes, it had to read a complete block. And when we're doing single partition reads, we're losing a lot of that information. So should range scans always be used when we're talking? So the answer is no. It's not a silver bullet solution. There are cases when you have very little partitions. And the range scans will do lookups in the index files and find out, no, there are no partitions for this range. So you did queries that are not needed. Yet, let's try to answer another question. Let's say that I'm trying to do a partial scan. What if I wanted to know the minimum, maximum over the last 7 days, or 30 days, or 90 days? When should I switch between one model and the second? So when we talk about partial scans, what we actually want to add is this date and allowed filtering at the end. Now, if you run this right now, it won't work, but we'll fix it. So let's look at the numbers. So single partition has 2.3 million I/O operations, and the range scans total I/O operations are 14,000. So that's 0.6. If we're talking about the total bytes read, it was 17.7 gigabytes versus 1.3 gigabytes. So everything lower than 92% of the data, okay? If I'm talking about 90%, I'm only interested in 10% of the data, then I should use full scans. I'll be reading less information off the disk. And in our use case, 7% seems correct. So if the partial scan would request getting back less than 7% of the partitions, you should use single partitions. And if it's doing more, then you should do a full scan. Although you'll be reading all the data, it will be more optimal, as I showed you. So in the general case, this was for Billy and the IoT application, it really boils down to how big are the partitions. As the partitions are larger, there is a higher penalty of reading unnecessary large partitions. So we deployed, we are on the beach with our long overdue vacation. We're drinking a mojito like this one, and we get a call. Well, you remember the partial scans and the full scans that we told you there will be around 200 an hour? Well, it turns out there are 200 a minute. Can you fix it? So one thing we can try to do is add pre-computed minimum and maximum for each day. It will be a background process that will need to update it, but we'll have that information stored, and we can use it. So for each partition, we're going to store a static field with a temp min and temp max. And when we talk about how to query that information, the query will be like this. So we want to get the min and max, but that's only one. We don't need all the rows. So Scylla 3.1 actually added per-partition limit. And per-partition limit means that for each partition, I'm interested only in a subset of the rows. In my case, I only need one, because the static fields are shared across the rows. So that is sufficient. So let's see, what will I gain when I run this? So if we compare the range scans to the pre-computed results, we can see that the data I/O dropped significantly, 3 times. And that is because we do not need to read the full partition. Okay, we read only the beginning of the partition that stores the static fields. And we do not need to continue reading. And the data bytes read is again dropped 3 times. Is that good enough? Well, someone needs to judge. if this is good enough or not. Another option is to have all those min and max stored in a different table. This will be better, but there is a higher cost. Well, when a day or sensor is removed, you need to do it in 2 tables. So there is a cost associated with that. So till now, I talked about data access and showed you some items, but part 2 of the talk will be about Scylla 3.1 and 3.2 additional features, again, specifically that can be used also in analytics. One item that we added, and some people mentioned that they're already using in production, is bypass cache. And Scylla cache is a read-through cache, which basically means that when you're doing a read of a partition, then we'll go to the mem tables, we'll go to the cache, ask if there is information for that query. If there is, we're going to merge it and return it back. If there's no information, we're going to go down to the SS tables, fetch the information, insert it into the cache, and only then compute, merge, and return the result. So that's a read-through cache. Bypass cache instructs Scylla not to do it to a query. So even if the cache has information, we're not going to use the cache information. We're going to go directly to the disk, read the information off the disk, and then when we return the information, it's not going to be inserted into the cache. And why should you use it? Well, it goes hand in hand with workload prioritization. So workload prioritization tries to assure you that your online workload can live with your analytics workload. That your analytics workload is not going to eat up all your disk or all your CPU, and your online workload is going to get its fair share. Bypass cache goes another step forward. It actually means that your offline workload is not going to pollute the cache, not influence the cache information. And only the online workload would do that, which is really what you really care, usually. I've talked about SQL per-partition limit that limits the number of rows returns per each partition key, and I have a small sample here. So the partition key, for each partition key, I have 2 rows. And when I run this query, I'm going to get the first row for each partition. And I've shown you how this can be used also if I'm storing information in static fields for each partition. SQL group by, so we use this in the first example for getting the information for every partition. And if we look at another example, so we have for each partition key, again, 2 rows with different values, and we're computing the min and max. So if I'm grouping based on the partition key, I'm going to take all those rows and compute the minimum and maximum, and so forth. I haven't shown this, but we also added SQLite. And SQLite is different than what is available in Cassandra. It's only on the coordinator node. There's no need to add any indexing. And if the primary key is a text field, like I have it set up, then doing this query will allow you to find all the partitions that have a suffix with 0 and are 2 letters. So to summarize, I hope I convinced you that disk access is a tool that you can use. So you can actually check your queries. What will be more efficient on a simple data set? Scylla 3.1 has bypass cache, which is a Scylla-only feature, and per-partition limit. Scylla 3.2 has introduced tracing with disk access, so how many I/O operations we're doing and how many bytes we're reading back. In SQL, we added SQL group by, like, and I haven't covered it, but also non-frozen UDTs, which is an interesting option. Last, optimize full scans, even if you're interested in partial of the information, can be much more efficient than doing single partitions.